Well, good morning. I'm here to welcome you to actually our first colloquium of the spring semester, and I'm introducing Dr. Meng Guo.
Yes.
Practice.
Very.
And Dr. Guo started her graduate career at the University of Maryland working with Bill McDonough. She worked on the distribution and abundance of uranium and thorium in the Earth. I assume it's in the early Earth, but in the Earth.
In the Earth, yeah.
She then moved to Yale for a PhD working with Jun Korinaga on the physics and chemistry of the crust-mantle differentiation. She has taken that a little bit further as she is a postdoctoral associate right now at Yale, where she's working on integrating the crust-mantle-ocean and atmosphere system, trying to address the question where we came from or how we got to now, is the way I like to phrase it. And without much longer of an introduction, I'm going to introduce Dr. Meng Guo, who is going to talk on the Deciphering the Habitability of the Early Earth, Insights from the Coupled Evolution of the Crust-Mantle-Atmosphere-Ocean System.
Thank you very much. Honestly, I didn't realize how long is my title until Professor White said it, but thank you very much for the kind introduction. My name is Meng Guo. So I am a geophysicist who is very interested in the early Earth's habitability. And through my work, I hope eventually I can delineate a habitable boundary on the Earth system. At the same time, I would like to provide a quantitative platform for geoscientists to conduct multidisciplinary research. So, okay. Sorry, wait a sec. It's not working, but that's okay.
You should just hit the arrow button on the keyboard.
Okay, cool. Sounds nice. Right. So we all know that the evidence of life can be traced back to the very first two geological eons. The unequivocal data of life can be dated back to 3.8 billion years ago. And this record can even push back to the Hadean, which is around 4.1 billion years ago. So what is really interesting to me is how would the early Earth look like, and how could it facilitate the origin of life? Okay. And there has been two very popular theories about origin of life. One is Darwin's warm little pond theory. So these warm little ponds allows for the long-term polymerization through the seasonal wet-dry cycles. And the other theory is the hydrothermal system theory, which suggests that life originated from the deep sea hydrothermal vents. And as you can imagine, that each of these theories requires certain surface environment on Earth to facilitate. For the warm little pond theory to work, we need to have stable landmass as well as suitable inland water environment in the early Earth. And on the other hand, for the hydrothermal system theory to work, we need to have the ocean pH, the alkalinity, and the redox state to reasonably match the condition that can facilitate life. However, we all know that the direct evidence from the early Earth are known to be scarce. That's why Hadean are called Hadean, right? And despite the recent development, there are still much debate regarding the exact physical condition in the early Earth. For example, the surface temperature estimates ranging from icy to hot, and the ocean pH has been reported ranging from strongly acidic to alkaline, and surface condition can either be subaerial or underwater. Okay, from my point of view, I think to understand the early Earth's habitability, we need to rely on the understanding of the intrinsic interactions among ocean, the atmosphere, and solid Earth system evolution. What demonstrated here is let me just try this. Okay, it's a simple illustration about how the solid Earth differentiation changes the surface environment composition. So to begin with, during crust-mantle differentiation, incompatible elements like potassium, thorium, uranium, hafnium, and neodymium, they tend to migrate into the crust. This redistribute the incompatible elements among the solid Earth system, make continental crust more enriched, and the mantle more depleted. And second of all, through mantle magmatism, gases like carbon dioxide, they can be emitted from the mantle into the atmosphere and ocean during plume, mid-ocean ridge basalt, and back arc systems. These alter the chemical evolution in both atmosphere and the ocean. And lastly, through weathering process and erosion process, interactions between Earth's crust and the ocean and the atmosphere further alter the chemical composition. So I think the chemical signatures that documented at the Earth's surface tell us the history about how Earth has developed to today's, to the Earth that we know it today. So my focus to study the early Earth's habitability have main three focuses. First, I would like to further our understanding regarding the history of continental formation, not only for its mass evolution, but also for its compositional evolution. And second of all, the ocean pH, alkalinity, and redox state is a very important point to build a habitable Earth. And lastly, I would like to explore the compositional evolution in the atmosphere with the consideration of planetary evolution and the presence with or without life. So let's dive into the first aspect, which is my main focus during my PhD work. So Earth, as we know, is the only planet among the solar system that have developed this dual crustal system, which provide a more diverse environment for life. And what presented here is a diagram that shows all the proposed continental evolution patterns, where the x-axis means time, 0 is present day, and 4.5 is the initial of Earth's history. The y-axis is the continental crust mass versus its today's mass. So when y equal to 1, meaning the continental crust has already developed to today's volume. And when y equal to 0, meaning there is no crust existing on the Earth's surface. And we can see that from this figure, we have no consensus on how the continental evolution happened during the Earth's history. However, whether if there is early crust on the Earth's surface is an important factor to examine the geological foundation for the warm little pond theory. Not only that, we also didn't know the early composition of the continental crust. We can see important papers keep publishing on both sides of the debate. Even papers using similar sedimentary rock constraints can arrive on different sides of the debate. However, the composition of the early continental crust can be an important indicator for whether there could be life on the early Earth or not. The reason for that is the felsic composition of the continental crust. Felsic means it's more evolved in composition. You can hardly directly get them from melting the mantle. To generate felsic continental crust, you need to have oceanic crust first, subduct it, and remelt it. These processes typically happen at the back arc system, which is associated with plate tectonics. Plate tectonics is very important for the development of life for two reasons. So first of all, through plate tectonics, it can resurface the Earth with a fresh bunch of nutrients. This is important to provide the growth-limiting nutrients to the bottom, to the surface of the Earth. And second of all, greenhouse gases like carbon dioxide, they can be recycled through subduction back into the mantle. This is very essential to convert the initially carbon dioxide-enriched atmosphere into a habitable one during the deep time. And lastly, the felsic composition of continental crust is also likely to provide a high potassium concentration that is beneficial for the development of life. We know that all living cells today has a high intracellular potassium concentration. If this potassium is not acquired after the origin of life, this suggests that life may also emerge from an environment that has high potassium. Hansma 2010 have proposed that this life may have emerged in between the mica sheets, which can mimic this high intracellular potassium environment. So, where do one people find such high potassium environment in the early Earth? And one possible direction to go is the early felsic composition continental crust. What presented here is one popular way to constrain the continental evolution history, which is using the geochemical box models. Geochemical box models utilize the complementary nature between mantle and the crust to constrain the continental evolution history, thereby considered as the most direct way. At the same time, it's not so expensive to run them, so it has been a popular modeling scheme. What demonstrated here is a very simple box model. We consider two reservoirs here, atmosphere and mantle. They are represented by boxes, and by parameting the arrow, which represents argon transferred between them, we can track the compositional evolution in both atmosphere and the mantle. At the same time, box models are associated with certain limitations. The first one is geochemical box models tend to utilize only one kind of constraint, which is the geochemical signature of selected isotope system. However, constraints coming from geophysics and petrology can also bring different and complementary constraints to the history of continental formation. And second of all, box models tend to assume instantaneous mixing within each box, which means each reservoir at all time only have one composition. This is such a strong assumption and neglects certain effects like finite time mixing in the mantle. So what I would like to present next is several geochemical box models that I developed to study the continental formation. Through these studies, I provide a step forward towards a more comprehensive understanding of how the continental crust was manifest on the Earth's surface, at the same time provide a step towards for a more accurate modeling scheme. The first model I would like to present is when I use the argon ratio in the atmosphere to study the continental evolution history. What presented here is a simple modeling scheme. So through the Earth's history, we consider two kinds of degassing phases. The first one is the sudden degassing phase, which during this time, a large amount of primordial argon can be degassed from the mantle into the atmosphere. This sudden degassing event is likely to have been introduced by the moon-forming giant impact. After the sudden degassing event, Earth entering this continuous degassing phase, when mantle can degas its argon into the atmosphere during the generation of continental crust. Crust can degas its argon into the atmosphere through the operation of crustal recycling and reworking. At the same time, the parent element potassium continuously to decay into argon, replenish the reservoir of radiogenic argon, and potassium can also be transferred from the mantle into the crust during crustal generation. Part of it can also be recycled back into the mantle. So, as you can imagine, how to parameterize the argon degassing rate through this geological process is the key to the success with this kind of modeling. And what made my model unique is I was the first one to systematically constrain the crustal recycling and reworking rate through time using the global detrital zircon dataset. So first of all, a bit of background knowledge. We all know that recycling means the loss of continental crust mass into the mantle through processes like subduction and delamination. Oh my God, okay. And at the same time, crustal reworking refers to all the process that can reset the apparent age of the crust. So you have some old crust, through like a partial melting, like intracrust melting, sedimentation, metamorphism, erosion, you make them appear younger by reading from the isotope system in it. Crustal recycling changed the mass of both crust and the mantle. Reworking only happens within the crust and there's no effect to the net growth of continental crust. And this is our modeling scheme to constrain the crustal recycling and reworking rate. So what demonstrate here, again, on the x-axis is time. 0 is present day, 4.5 is the initial of Earth's history. The y-axis is still the continental crust mass versus its today's mass. So the yellow solid line is one example of the net continental growth model. This represents a continental crust that presented on the Earth's surface through time. The blue dashed line and the red dashed line are the present day's formation age and surface age distribution of continental crust. These two lines come from the global detrital zircon database, and they are internally consistent with each other. So, okay, it doesn't work. So if we liken the night growth model of continental crust as an intact apple, meaning it represents all the crust that ever exist on the Earth's surface, then today's formation age distribution is like an apple that had been beaten by plate tectonics. The missing part of the apple tells us how many crust has been recycled back into the mantle. So knowing their differences, we can model the corresponding crustal recycling rate over time. In similar fashion, crustal reworking make the continental crust age change. And by knowing the surface age distribution and the formation age distribution, we can model the corresponding recycling rate over time. Okay. So by using this model, we not only constrain the argon evolution in the atmosphere using geochemical constraints, but also incorporated petrological constraints to infer the crustal recycling and reworking rate. This presents as a more self-consistent approach to evaluating multidisciplinary data. So let's dive into how we exactly achieve this. In this equation here, M denotes the instantaneous formation age distribution of the continental crust, where T means time and tau means formation age. Okay. So the process of crustal generation and recycling can both modify the formation age distribution. For that, crustal generation add to the total mass of a crust formed at this time, and the recycling decrease it. Today's cumulative formation age distribution can be obtained by integrating the instantaneous formation age over tau at present day time. After we obtain this cumulative formation age distribution, this result is compared with the global data zircon site data. Yeah. And in a similar fashion, we model the crustal reworking rate. So in this equation here, S becomes instantaneous surface age, tau becomes surface age, and T is still time. Crustal generation and recycling again modify the surface age distribution, and the reworking, it adds to the mass of the crust that appears to be younger and decrease the mass of the old crust that has been weathered. As a result, similarly, the cumulative surface age distribution can be obtained by integrating S over tau at the present day level. Not only for that, we also use the argon ratio in the Archean and present day atmosphere to constrain the rate of chemical differentiation within the solid Earth. We use the mantle potential temperature history to constrain the rate of thermal evolution in the mantle, which further give us the rate of mantle plume degassing as well as the degassing during the generation of oceanic crust. And as explained before, we use the formation and surface age distribution to constrain recycling and reworking rate. I conduct a Monte Carlo simulation. The final successful result, which is showing in green here, they need to satisfy all these observations within reasonable uncertainty. Okay, this is crazy. Okay. At the same time, the continental formation history that met with all these observations are presented in here. First of all, this is the night growth model of continental crust. From this, we can see that during the Hadean, we experience lots of generation of continental crust, with 80% of stable crust mass exists in the early Archean. At the same time, during the Hadean, we experienced intensive crustal generation, recycling, and reworking rate. This causes intensive degassing from both the mantle and the continental crust, and this is the drive for us to match the Archean argon ratio in the atmosphere. Lastly, I was curious about how each physical process that can contribute to the radiogenic argon inventory in the atmosphere. What we see first is the generation of continental crust contributes the most to the radiogenic argon in the atmosphere, which makes sense because in the early Earth, most of the potassium resides in the continental crust. But more interestingly, we find continental crust also offers lots of radiogenic argon to the atmosphere through the process of recycling and reworking. Argon-40 is a decay product from potassium, which is an incompatible element only abundant in the felsic continental crust. So because of that, our result tells me that a significant amount of felsic continental crust already exists in the early Archean. At this point, you may still recall there are two kinds of limitations associated with geochemical box model. We use argon to address the limitation with to incorporate multidisciplinary data into geochemical box modeling. The second limitation is box models tend to assume instantaneous mixing within each reservoir, and this means every reservoir only have one composition at a time. However, these depleted mantle signals may be delayed by considering finite time mixing effect in the mantle. So what do I mean by finite time mixing effect? It means during crust-mantle differentiation, crust was extracted from the mantle, and the corresponding depleted mantle signature is carried by the depleted residues. These residues have a higher solidus and are resistant to be remelted. Therefore, they become undetectable to the Earth's surface because it doesn't contribute to the basalt archive. We have to mix them with the surrounding more enriched mantle in order for them to remelt again. Naturally, this creates a mismatch or a time lag between the actual mantle composition versus the composition you observe in mid-ocean ridge basalt. I find that this concept is very much like making a cookie dough in your kitchen. You mix the chocolate chips in your cookie, it takes time to mix them, and before you can actually take a scoop of cookie dough that have decent amount of chocolate in it, time has passed, okay? And this tells us convective mixing, like mixing the cookie dough in your kitchen, takes time to complete. And this effect really important to how the depleted mantle signature was manifest on the Earth's surface. However, incorporating this physical common sense into geochemical box modeling can be challenging due to it requires more sophisticated modeling effort, and it has remained as a challenging task for us for centuries. For decades, yeah. And I developed this box model, but with finite time mixing effect incorporated. And we use this one to analyze the epsilon hafnium and neodymium signature generated in depleted mantle during crustal formation. A little bit background knowledge here. So for the lutetium, hafnium, and neodymium isotope system, the parent element, lutetium and samarium, even though they're also incompatible, but compared to their daughter elements, they prefer to stay in the mantle. Hafnium and neodymium, on the other hand, like to go through the crust. So over time, during crustal formation, the epsilon hafnium and neodymium signature become positive in the mantle and become negative in the crust. And I would like to walk you through our modeling scheme. So we think the generation of continental crust from mantle takes two steps. Mantle melt first to generate a protocrust and leave a very depleted mantle residue in the mantle. Protocrust melts again to generate continental crust and also leaves a depleted crust residue behind. Continental crust can be recycled into the mantle. So all three components contribute to the whole mantle composition during crustal formation. And some of them are so depleted they are resistant to remelt, and others can be very cold and takes time to warm up to remelt. Each of them can delay the depleted mantle signature that we see in the basaltic archive. Why? Okay. And how do we modeling the stretching of this heterogeneity in the mantle is the key to the success of this model. So this is a simple illustration. We first consider that the heterogeneities, like crust and mantle residues, they are introduced into the mantle as a blob. But the physical shape of this blob does not matter. Only thing matter is the thickness. Over time, mantle convex. This stretch this blob into thin laminars. This is much like when a Chinese chef making a noodle from a flour dough. Eventually, this heterogeneity is stretched into fine, thin laminar, and when its thickness below a certain critical point, we consider they are well mixed and they can start to remelt. Now, we randomly place the sampling box everywhere in the mantle to assess the composition of the mantle that can remelt. Each sampling box represents one melting event, during which mid-ocean ridge basalt are generated. By analyzing the composition in each sampling box, we can assess the degree of heterogeneity in the mantle. And the key success is to factor how the stretching in the mantle changes with time. So we see the length of a heterogeneity at one time is proportional to its original length, the time passing in the mantle, as well as the strain rate in the mantle. The strain rate in the mantle can be related to the change of plate velocity. And we use empirical data to constrain the mantle potential temperature changing with time, which gives us the plate velocity evolution. And lastly, it controls how fast the heterogeneities are stretched into the mantle. Using this model, we test the different scenarios of continental generation and try to reproduce the depleted mantle signature we observe on the Earth's surface. The figure here, again, x-axis is time, 0 is present day, 4.5 is the initial of Earth's history. The y-axis is epsilon hafnium and neodymium signature in the depleted mantle. The blue dots, they are actual signatures coming from mid-ocean ridge basalt. And what we can see here seems like epsilon hafnium and neodymium suggest depleted mantle are started to generate from 3.8 billion years ago. So what do we traditionally interpret this result? We say depleted mantle was generated in the Archean. So continental crust must also only extracted from the beginning of the Archean. And we test a scenario when continental crust extracted from the beginning of Earth's history. And the corresponding modeling simulation, which is shown in red here, tells us the epsilon hafnium and neodymium signature created in the Hadean does not show up on the surface after 0.7 billion years ago because we consider the effect of finite time mixing in the mantle. By incorporating this physical common sense into geochemical box modeling, it becomes a game changer for the whole box modeling scheme. At the same time, it changes people's interpretation of geochemical observations. So, to sum, what do we know about early continental crust? The answer is yes, we probably have them since the beginning of the Earth's history, and their composition is likely to be felsic. The implication to that, the early massive continental crust generated on the Earth's surface provide a necessary environment for the warm little pond theory to work. At the same time, the potassium-rich environment also enables the development of life on a certain degree. Lastly, the existence of operation of plate velocity is called for, plate tectonics is called for to explain this massive felsic continental crust. And it's also essential for stabilizing the early climate and provide nutrients for the development of life. And then I also trying to evaluate the ocean pH in the Asian Ocean, and this is my first attempt, but I would like to share some of my findings. So why do I recognize ocean pH is such an important factor for building a habitable planet? This is because, generally speaking, the life as we know it today can hardly directly originate from acidic conditions. For example, RNAs are subject to hydrolysis and also modification of their functional group in acidic environment. At the same time, the formation of ATP, which is a major source of energy that drives biochemical reactions, is also hindered during acidic ocean. As a result, to examine the ocean pH in the inland and ocean water is an important geological foundation to see how life has developed on Earth. So how do we achieve that? There are many ways to calculate the ocean pH. One possible way is to use direct proxies like boron isotopes and alkanones. However, because I am interested in the Hadean, and due to the poor preservation of empirical data, direct proxies are not really available. A second way is to calculate ocean pH from the partial pressure of carbon dioxide. Again, because the long time scale we are interested in, and we also do not have consensus about how the carbon dioxide change in the atmosphere, this results in a large range of estimated ocean pH. Lastly, theoretical studies have suggested that the early ocean can either be alkaline, acidic, or approximately neutral because we all make assumptions of the relative importance between the source of acidity and alkalinity. However, due to the ambiguity in modeling this exchange, we are not making any agreements here. What I want to present to you is a statistical model that we use to calculate ocean pH by combining it with a global carbon cycle model I developed. So first of all, we can calculate the concentration of hydrogen in the seawater through time through solving for marine charge balance. The major ion concentrations in the seawater, we can model their concentration over time by calculating for their geological sinks and sources. The partial pressure of carbon dioxide in the atmosphere should provide us the concentration of carbonic ions. Lastly, we prescribe some minor ion concentrations in the seawater to get us the concentration of hydrogen, from which we get the ocean pH. The important thing is we incorporate a global carbon cycle model to systematically constrain the PCO2 level change in the atmosphere. So what demonstrated here is a simple modeling scheme where we consider 4 reservoirs: continental crust, ocean anticrust, mantle, atmosphere, and ocean. So these arrows means the physical exchange of carbon among these silicated reservoirs. And the rate of it is guided by the thermal evolution of the mantle and the formation evolution of the continental crust. By doing this, we were able to not only constrain the global carbon cycle, at the same time, it also gives us the geological sinks and sources of the major ion concentrations in the seawater. In the end, it provides a self-consistent modeling scheme to systematically constrain ocean pH, and we were able to using the Earth's interior process to guide the physical rate of carbon transformation on the Earth's surface. The successful results through Monte Carlo simulation not only have to pass all the constraints that we presented before to constrain the formation history of continental crust, they also need to pass through the constraints of partial pressure of carbon dioxide in the Precambrian and present day, ocean pH at present day, surface temperature at present day. So what do we know from this result is Earth seems to have experienced massive change during the very first 500 million years, with partial pressure of carbon dioxide decreased from nearly 200 bar to 10 to the negative 2 bar by the end of Hadean. As a corresponding result, the ocean pH evolved from strongly acidic to approximately neutral. This marks the ocean that become more habitable for life and is almost 1.5 billion years earlier compared to previously proposed. Lastly, the surface temperature dropped significantly from 230 degrees to almost freezing point at the end of Hadean. So you may wonder, what drives this massive change in the early Earth? What plotted here is the evolution it's the evolution of continental weathering rate and seafloor weathering rate through time. Again, x-axis is time, y-axis is the each rate to the log 10 scale. So what we see is during Hadean, seafloor and continental weathering rate is almost 1 to 2 magnitudes higher compared to the rest of the Earth's history. And the reason for that is seafloor weathering is controlled by the rate of plate velocity as well as the abundance of carbon dioxide on the Earth's surface. Continental weathering is also constrained by the carbon dioxide on the Earth's surface, at the same time also the surface temperature. In the Hadean, when Earth was first solidified after magma ocean solidification, the mantle was characterized by instability due to the solidification effect. This allows for faster plate velocity in the Hadean and brings a fresh bunch of silicated rock to the Earth's surface, who is subject to be weathered. At the same time, the global temperature at the surface was high. We have almost unlimited supply of carbon dioxide on the surface. Both of them enhance the weathering ability in both the continental crust and seafloor. And in turn, they remodify the carbon dioxide concentration in the surface and make Earth become more habitable through time. And the implication of this study is, as we mentioned before, Earth's life as we know it today can hardly originate directly from acidic water. And we have empirical data as the evidence of life dated back to 3.8 billion years ago. However, previous study tells us the ocean does not become habitable until the end of Archean. Our model was able to tell us that by the end of the Hadean, the atmospheric partial pressure of carbon dioxide has decreased to a reasonably low level, and which controls the pH in both the ocean and the inland water environment, provide the necessary geological foundation for the origin of life theories. Lastly, I would like to not bore you with another geochemical box model I do, but rather a statistical model, from which we constrain the halogen abundance in the bauxite Earth and infer its degassing history through mental differentiation. So this project is very personal to me, and I will tell you why. I initially wanted to do a halogen global cycle model because it constrains that seawater alkalinity, acidity, and it's important for the origin of life. But what's the first step you do when you do a global, box model? You check for global mass balance. And what I find is very interesting, that the previous estimates of halogen abundance in the bauxite Earth is smaller than the halogen abundance in the other reservoirs summed up. And one thing is, who make this bauxite Earth model? This is my master degree advisor. This is my PhD degree advisor. So when I encounter this problem, I feel like, okay, this is interesting. I have to solve it. Another thing is, I don't know where to start, because any of these compositional models could have been the source of problem, any one of them or two of them or three of them. And then I have encountered this paper, Clay et al. 2017. So what demonstrated here on the x-axis is the condensation temperature of the element. The y-axis is the element abundance in the bauxite Earth that is normalized to Ci contract and magnesium. And this paper tells us the heavy halogens, if you use the previous bauxite Earth model, they seem to be very depleted compared to other elements with the similar volatility. And this have evoked a massive explanation about halogen needs to behave differently when solar nebula condense. However, we all seem to accept that the halogen abundance in the bauxite Earth model must be correct. So how did they estimate that? One common way used in the bauxite Earth model is called constant ratio method. This method assumes that the halogen abundance versus another element's abundance in their basalt must be the same ratio that they observe in the mantle source region. However, if you really think about it, how do you generate basalt from the source mantle? You first need to melt it, and then the melt needs to crystallize into basalt. In either process, the two elements can be redistributed according to their bulk partition coefficient. So I start to calculate the primary melt composition from the basalt by assuming it went through crystallization. And already I have obtained a different ratio of halogen to a trace element compared to their ratio in the basalt. Then I calculate the source mantle composition from the primary basalt by assuming it went through melting. And again, we arrive in a halogen concentration that is much higher in the source mantle compared to if you use a constant ratio method. So we can see that the constant ratio method only works if these two elements that we're interested in have exactly the same partition coefficient, doing both melting and crystallization. And you can imagine how hard it is to achieve. So another way to go is and we develop a new method called the log-log correlation method. And what compared here is from a real basalt data, we use the log-log correlation method, which perhaps mimic the melting trend, and compared to the constant ratio method, you can get a much halogen abundance in the source mantle. We tested many different element pairs and was able to reconstrain the halogen abundance in the bauxite Earth. This new model results in 2 to 3 times higher halogen abundance compared to previous studies. And as a result, the global mass balance is restored. The implication for that is, by using our new constraint of bauxite Earth composition, that halogen, especially the heavy halogen, are not so depleted compared to other elements within similar volatility. This suggests sufficient halogen retention during the planetary formation process. And second of all, according to this constraint, majority of the halogen is still within today's mantle, suggesting halogen may have gone through intensive degassing in the early Earth, but gradually regassing through the rest of the Earth's history. Lastly, this constant ratio method is intensively used to constrain the element abundance in bauxite Earth model, continental crust model, and depleted mantle model. So some of these models may be subject to be revision. Moving onward, I would like to continue my study to understand the early Earth's habitability. In each of these areas, there are many efforts left to be done. For example, the thorium-uranium-lead decay system is extensively used in geochronology. However, it's associated with 2 different kinds of paradox. Some of them may be solved by considering finite time mixing effect in the box model. Strontium may have a better constraint on the crustal recycling rate, and as mentioned before, new statistical models of continental crust and depleted mantle may be revised. And lastly, by incorporating age-dependent modeling of recycling and reworking, we can provide a better modeling scheme towards geochemical box models. I tried my first attempt to constrain the ocean pH in the past, but it can also be remodified and improved by incorporating improved modeling of major metal ion cycles. At the same time, there are other important elements in the seawater is left to be discovered, for example, phosphate. And lastly, because sulfur, nitrogen, they act like the growing limit elements at today's for the development of life. So by studying their global cycle may be beneficial to understand the early Earth's habitability. And looking ahead, I will embark a collaborative journey. By working with geobiologists, I hope to provide a guidebook of where are the possible locations on Earth that could facilitate life. And working with planetary scientists, I would like to cast a wilder net into the cosmos, asking the question are we alone? And as a modeler, my biggest interest is working side by side with geochemists and geologists to identify the new proxy of tracing continental formation history and find the evidence of early Earth surface condition. Lastly, as a geophysicist, I would like to continuously incorporate geophysical concepts into geochemical box modeling, provide a better modeling scheme for us to conduct multidisciplinary research. I would like to end my talk with a likely scenario of how I think Earth becomes habitable over time. So in the very beginning of the Earth's history, right after magma ocean solidifies, that the surface Earth is characterized by high partial pressure of carbon dioxide, which is nearly 200 bar. As a corresponding result, the surface ocean can be very acidic at that time and is hostile for life. The surface temperature can be as high as 230 degrees, and we started to see felsic composition continental crust appear on the Earth's surface. Due to the fast plate velocity tectonics, we see that massive crustal generation, recycling, and reworking happening on the Earth's surface. These have caused intensive degassing from both the mantle and the crust. At the same time, rapid plate tectonics is called for to explain such phenomena and have geophysical backbone to support it. Lastly, because the high surface temperature and the abundant supply of carbon dioxide, we can expect significant amount of silicated weathering on both the seafloor and continental crust. Now move to the end of Hadean. At this time, due to the efficient weathering, the carbon dioxide level in the atmosphere already decreased to a habitable level around 10 to the -2 bar. As a result, ocean pH rises to a moderately habitable condition, and surface temperature dropped significantly. At this time, maybe 50 to 90% of today's continental crust mass already exists on the Earth's surface. Because during the Hadean we have faster plate velocity, the heterogeneity in the mantle has been erased, so the plate velocity started to decrease. As a result, crustal generation, recycling, and reworking rate went down. And the mantle may started to regas some elements like halogen and water back into the mantle. Through this work, I was able to delineate a habitable boundary on the Earth's history to be within the late Hadean to early Archean. After the early Archean, Earth slowly developed to the home that we call it today. Okay, thank you so much for your talk. Thanks.
Thank you. And why don't we start with this half of the room? If anybody has a question, we'll start with the younger portion of the crowd. And Lauren, are you monitoring? Mark.
Hey, great talk. With the second part of your talk
Yeah.
about modeling pH, does it factor in changes to weathering over time in that, climate has changed, sea level exposure has changed? How fine scale is your model?
Yes, so how fine scale? I would say because I model the entire Earth's history and I want to make the model not so computationally expensive, so our time step is 0.1 million year. At the same time, we did incorporate about the mass evolution of the ocean to take into mind, but if you consider like studies from like magma ocean solidification, we have a shallow ocean to begin with. And by studying continental freeboard model, that's how we constrain how the ocean mass evolve with time. Did I answer your first part of the question? Okay, cool, thank you.
Ronan.
In your opinion, like you're talking about time scales on Earth, like so the Earth reached a period where you had a certain pH and temperature in the acidity. Do you think life started basically at that point?
That's a very hard question to answer because how do you know if there is really life back in time? You have to rely on empirical data. And as we said in the talk, the unequivocal data, like you cannot argue, only goes back to 3.8 billion years ago. But if you study like some carbon isotopes and trying to infer maybe there's also life back in the Hadean, that starts around 4.1 billion years ago. I think as a geophysicist, I can only do my best to constrain when does Earth become habitable. I cannot say when the life beginning in the Earth's history unless I start to work with a geobiologist. Yeah, thanks.
Online, Bob and I think Claude have questions.
Okay. Do you want to ask it or they want to
No,
unmute?
they're going to say, so I guess Bob's just unmuted.
Okay. Can you all hear me?
Yes.
Okay. Thanks, Meng. That's a very interesting talk. I may have missed it when thinking about your ocean pH study, but when you mentioned data constraints, I think I saw in your plots like late Precambrian data constraints, but what is the available data to actually constrain what's happening in the first several hundred million years of your model where all the excitement is?
I agree. Like, because the empirical data, like we used to constrain ocean pH, relies on the partial pressure of carbon dioxide. So if you can see my slides, we have Precambrian data of carbon dioxide back then. However, it doesn't put any strong constraints for the initial of the pH change and carbon dioxide level change in the Hadean. But we know that from magma ocean studies that in the early Earth, after magma ocean solidification, you have lot of amount of carbon dioxide in the atmosphere. So the real problem is how do you subtract that amount of carbon dioxide so quickly, like during the Archean. And the reason for why we have a temporal change of the PCO2 subduction is because our plate velocity rate started to weighing down. And because plate velocity constrains both the weathering rate in continental crust and mantle, so physically you cannot subduct lots of carbon after the Hadean. So this this massive change have to happen in the not in the Archean, but in the Hadean. But you are right, we do not currently have empirical constraints on this. That's also why I said in the future study, I would like to identify, if possible, new proxies for the early Earth physical condition. Yeah.
Thanks. So what are the major free parameters? And I can't see the room, so Jen, please cut me off if I'm holding up your cue.
Right.
But if what are sort of the major free parameters that we would like to know in order to understand that better? It's C4. It's basically a C4 weathering rate. And
Yeah.
that's right now coming from magma ocean theory model, or tell me more about it.
I think the first important thing is whether we have continental weathering in the early Earth to begin with. If you have no continental crust, basically you don't have this contribution at all. So one free parameter would be the fraction of land mass on the early Earth's surface. At the same time, the early Earth temperature is also very hard to constrain. So I would say that's a degree of freedom in our model. So in this model, I developed a 1D two-layer gray atmosphere to constrain the changing temperature on the Earth's surface. But I would also agree there is lots of room to improve on this model, and the temperature give a large contribution about how much silicate rock on the continental floor you can weather. So I think that's the degree of freedom I see that contribute biggest to our modeling result.
Thank you.
Thanks.
Claude? Or
Now, Meng,
Yeah.
main planners were here. I'm sorry I couldn't be there in person. I enjoyed your talk. And so what I'm seeing, and I read your paper too with Jun, all these changes at the Archean-Hadean boundary. You've got the Hadean is very active, very fast recycling rate. High plate velocities, and very high weathering. So I'm trying to picture what the mantle was going through as it went from the Hadean into the Archean. Can you kind of give us a picture? What accounts for these drastic changes? Why wasn't it, for example, a gradual changes from the Hadean into the Archean? Why were these sort of major discontinuity? Yeah, look at your rates. Yeah, that's a great diagram. Yeah, look at your rates in terms of. So how do you explain that major changes going on?
I see. Yes. So answer your first question, what really changed in the mantle during the Hadean is, after magma ocean solidifies, by considering the different solids, you will expect mantle was very heterogeneous at that time. It characterized by a high mg number ambient mantle and having a high iron-rich a blob in between, and this caused instability and caused the mantle to move. At the same time, considering the partition coefficients of carbon dioxide and water in a magma ocean, after magma ocean solidifies, lots of the water is in mantle, and Earth's surface is only characterized by a shallow ocean. Because mantle was very wet and it was hot, so they can fast move. But after the end of Hadean, because you only have so much water in the mantle to degas. During the faster plate velocity, lots of water was degassed. So after the Hadean, not exactly after Hadean, but in this period of time, mantle becomes dry. So mantle plate velocity slows down. Another line of evidence comes from where this mantle started to melt. If you melt at a deeper depth, you result in a thicker continental lithosphere. It's more resistant to be subducted. And in the early Earth, you melt at a shallower depth because this heterogeneity. So you also have a shallower depth of continental lithosphere, which is very easy to break down and subduct. So I would say the change for this a faster change of plate velocity comes from one, mantle was heterogeneous heterogeneous to begin with and slowly become homogeneous. And two, that mantle have lots of water in the beginning of the Earth's history and lots of water by the end of Hadean. Does that answer your question?
That was really helpful, yeah. Yeah. But one last thing, at what time in the Hadean in your model did the magma ocean solidify, or like it was more or less completely solidified?
Yeah.
Very early on in the Hadean or now? I mean, there's a wide range of estimates there.
Oh, yeah. So actually, I shouldn't mark at 4.56 billion years because actually my ocean model started at like 4.5. So this period of time, we estimate within like 30, 50, like a million years. So I should mark it here around like 4.51, 4.52. Similar at the end of like a giant impacts.
Okay, well, that's a great help. You give me a lot to think about. Thank you very much, Meng.
Thank you.
Ben, and why don't you repeat his question? I don't think they can hear the question, but Ben?
Hi, thanks for an interesting talk. I was curious, you highlighted in terms of your future directions working with planetary scientists, so I'd be interested to hear more about the opportunities you see for applying this kind of clock modeling approach to other rocky bodies, but also exoplanets.
Yeah, so my thinking of that now is like a very first attempt is because, for example, Venus and Mars, they are characterized by having lots of nitrogen. On the other hand, Earth started to have much less of them. Before the beginning of life, the nitrogen cycle is primarily constrained by the solid reservoir differentiation. So by understanding the nitrogen cycle in the early Earth and compare to the nitrogen cycle change in other planets like Mars, Venus, exoplanets, I was hoping to get information about the early degassing and differentiation process on other rocky bodies. Yeah, but that's also why I want to work with geobiologists to understand how the presence of life modify these element cycles to better help us understand what presence of life means to us, you know. As of course we all lives, but yeah.
Any other questions online, Lauren?
Can I talk?
Yes.
Okay, so via the nitrogen cycle. So the issue of nitrogen is related to hydrogen.
Oh no, I just showing multiple project idea. Is this what you mean?
No, I'm not talking about that especially. Okay. I'm talking about the gravitational way in which a planet can contain hydrogen.
Okay.
So N2 is the gas on Earth. NH3 is the gas on Jupiter, for example. They're related to the gravitational way in which a planet can contain hydrogen.
Okay.
It's a very interesting problem because the hydrogen cycle on Earth is only related to biology. And the hydrogen cycle on Jupiter is totally independent of biology, obviously. So let's think a little bit about something related to biology. So the origin of life on Earth had to make nitrogen available for biology early on.
Yeah.
There maybe lightning was something, but somewhere early on, and I don't know when is the earliest on, but it had to be very early on, biology had to invent nitrogen fixation. You have any thoughts about that?
Okay, so what's the question? So so if that's what you mean, you need to do a hydrogen cycle together with nitrogen cycle with and without the consideration of how does life affect this cycle. I agree with you, but I feel also like a hydrogen cycle in the early Earth also depends on how fast the place was moving, mantle degassed, and how much was subducted back into the mantle. So both cycles initially should be constrained by the physical separation of crust and mantle, and later on will be constrained by the presence of life. So by factoring all these factors into a model, we can get their co-variation through time, and that maybe have some implication for the origin of life study. I hope that answers your question, but if not, feel free to let me know.
No, it doesn't answer my question. It just gives us a way to think about working together.
Oh, okay. Thank you.
My answer would have been I would have called Paul Falkowski and asked him what he thought. Oh, wait, he's asking the question.
Oh, okay. Yeah.
No.
Yeah, like if in that line, I actually think another important cycle to incorporate is phosphate because it's a growth limiting element, and I don't think lots of people ever done this kind of study in this aspect because the pH is poorly constrained. So yeah, like if you are thinking about future collaboration, I would very much like to contribute to that, and also maybe also including like the phosphate cycle. Yes, thank you.
Well, so Jiwa Hao, who was one of my postdocs a little while ago,
Right.
Worked on the phosphate cycle in the Earth. But you know, at the end of the day, phosphate is an acid-base reaction, and all the other elements of the big six, hydrogen, carbon, nitrogen, sulfur, and oxygen, they're redox reactions.
Okay.
So electron transfers are not just simple things in geology. They're things that are mediated by biology.
Good to know. Okay.
All right. Thank you very much.
Okay. Thank you.